Hey guys, this is Mr. K, and we're back with chemistry this time. Something a little bit different than biology, but before you have biology, you need to have chemistry. So let's talk about chemistry. Anyways, um, have you ever heard of matter? What is it? Basically, matter is anything that takes up space and has some mass to it. Some of you may have heard of dark matter, which is an unknown thing in our universe that accounts for most of the mass of our universe. We don't know what it is. But the matter that we're going to be dealing with are everyday atoms and things that have mass, and they make up everything that you see around you. You may have heard of elements before. And again, what is an element? It's basically the simplest form of a substance that cannot be broken down, and but it still retains all of the properties of that particular element. So oxygen, lead, gold, chlorine, sodium, bromine, any of these things are elements. Now, when we combine two or more elements together, we get something called a compound. And in this example, we're taking sodium and we're taking chlorine, and we get salt or table salt, which is something that you are familiar with. Now, what's interesting about this is that pure sodium, if I took that little chunk of pure sodium that the man is holding on the left right there and threw it into water, it would explode violently. And consequently, if we took the chlorine, which is shown in the center photo, and we turned that into a gas, it would kill you. And this was a gas that was used during World War I, chlorine gas. Yet, when we put them together, we get something we use every single day and we need in our body, table salt. Now, this is an important concept, guys. When we combine two or more elements together, they unique properties will emerge, especially with things like ionic compounds. So that's a very important property. I want you to remember that. So there's a lot of elements out there. There's like 115, 118, something right around there. Can't remember right off the top of my head. But you need to know the six most important ones for life, and we can call them CHNOPS. That's carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. With these six elements, we can make up all of the major biological molecules that make up your body. And if you look at this graph over here, you can see that oxygen makes up 65% of our body. You're like, 65% is oxygen? What? How's that? How's that? Well, think about it. About 65% of your weight is water. What's water made up of? It's made up of two hydrogens and an oxygen molecule. So that's where most of that weight is coming from. Well, we see 65% of the human body. And then, of course, you see the other ones, the hydrogen and the carbon and nitrogen, and we'll be talking about those extensively. As you can see, our protons are in the center, and they have a positive charge. And then we have two neutrons, which are also in the center. They are neutral. You can see that in their name, neutrons, neutral. And then we have the electrons surrounding that. So here is we have the sodium element, and there you can see an atom of sodium on the on the left-hand side, and it has, as you can see, two electrons in the inner circle. Then it has a total of 8 electrons in the second energy level, and in the third energy level, it only has one. Now, it can have as many as 8 there. And if it only has one, there's a pretty good tendency it's going to lose that electron. And when it loses that electron, it becomes positive because the sodium atom on the left is neutral. and when it loses a negative electron, it becomes positive, and that's the sodium ion that you see on the right-hand side. When we look at atoms, we like to look at our periodic table, and I'll show you these in the classroom. And let's start at the very top. And you can see we have two atoms in the first that only has that only have electrons in the first shell. That's hydrogen and helium. Now, when we have two electrons in that first shell is full, and then additional electrons have to go into a different energy shell. So if we look at the second shell and look at the first element on the left-hand side, that is lithium, and it has 3 electrons. And as you can see, it has 2 in the first shell and 1 in the third. And if we go all the way over to the right-hand side of second shell, we can see neon. And neon has 2 in the first energy shell, and it has 8 in the second shell. And this is to play an important role because neon and helium and argon, which are all in that last column, all have full energy shells. And this is important because electrons are what cause molecules to react with each other. And if there's no available electrons or space to put any more electrons, then that molecule or that atom is said to be stable and it will not react with anything. And that's very different than what we see in the first column, which has hydrogen, lithium, and sodium, where there's only 1 electron in the outer shell. These have a tendency to lose their electrons very easily, and they are known to be very reactive. And the same thing with if we go over to the right-hand side of the column and look at the second to last column where fluorine and chlorine are located, and you can see they only have 7 of the total of 8 possible electrons in their outer shell. These elements are also highly reactive. They want to steal an electron from something. Okay, and what are they going to steal it from? They're going to steal it from something in the first column, which only has 1, which wants to get rid of its electron. So we'll be talking some more about that in the second half. So I just showed you the picture of these electrons in these little energy shells, as you can see in the bottom part of this diagram right here. But that is not really the way they occur in nature. In nature, they are in a cloud because these things are moving at the speed of light, and we can't say where they are because they're moving at the speed of light around this little tiny thing. Well, they move in certain what we call orbitals, though. And as you can see, we have the 1s orbital, which is small, the 2s orbital, which is a little bit bigger, and then we got these p orbitals. And they kind of look like these weird water drops, if you will, coming in and out at different angles. Well, these different types of orbitals have different levels of energy. And that's something we will get into a little bit later. But the main point I want you to get is that the electrons are going around the protons in these orbitals or these little electron clouds. So you've all heard of molecules, and molecules are when there are 2 or more atoms that are bonded to each other. And these elements or these atoms can be the same type of element as we see here in oxygen, which would make oxygen gas. That's what O2 is. See water, which is H2O. And we're going to talk about these types of bonds. This is actually what's called a covalent bond, which results in a sharing of electrons. And we will talk about this and this important molecule, water, in an upcoming lecture. The periodic table of elements. And what we need to realize here is how it's arranged. And basically, it goes from the top left-hand corner, which has hydrogen, all the way down to the bottom uh, right-hand corner, which has, I can't even know what that is, LR, at an atomic weight of 103. And basically what it's showing you is these elements are increasing in mass from 1 to 103. And we have other ones that are in there. As you can see, actually it goes up to 118, not 103. And that's UUO all the way on the right-hand side in the kind of yellowish section. So a couple of things about how to read one of these things, these periodic tables. And the first thing to look at is the symbol. This is, of course, the symbol for oxygen, which is O. And there's two numbers that you see on this. We see a bigger number of 15.9994, and we see a smaller number of 8. The 8 refers to the number of protons that is found in oxygen. And the 15.994 is oxygen's atomic mass, okay, and or atomic weight. We can call them both. The 8 refers to, again, as I said, the number of protons, which is the atomic number, and the mass number or atomic weight on the bottom is the larger number. And we can use this to tell us how many neutrons there are. Normally, there is an equal number of neutrons as there are protons. So protons and neutrons equal each other, and normally the number of electrons equals the number of protons. Because remember, neutrons do not have a charge, and electrons have a negative charge, and protons have a positive charge. And so overall, the element has no charge, so we have a balance when we have 8 protons and 8 electrons. But that's not always the case. So the way to figure out the number of neutrons is you take the atomic weight or the mass number on the bottom of 15.9994, or round it off to 16, and then subtract the number of protons, which is 8. So let's say 16 minus 8 gives me 8. There are 8 neutrons, 8 protons, and therefore 8 electrons. However, this number can change. You may have heard of isotopes, and isotopes are basically elements that have the same number of protons and generally the same number of electrons, but the number of neutrons changes. And remember, it's the number of protons that determines the characteristics or what defines an element. A carbon atom will always have six protons. It will always have 6 protons. However, the number of neutrons may change. And if we look down here at the bottom of this diagram, we see 3 different isotopes of carbon. We have carbon-12, which is normal carbon, has 6 protons, 6 neutrons, and 6 electrons. Carbon-13, it has 6 protons and 7 electrons. 13 is its atomic mass, so 13 minus 6 equals 7. And carbon-14, as you can see, that would be 14, its atomic weight or mass number, minus 6, and that would give us 8 protons. And the top picture is showing different types of hydrogen. And you may have heard of some of these hydrogens, like 888 hydrogen like tritium. And if you have a watch that glows in the dark, the hands and stuff that are glowing in the dark actually have this heavy hydrogen, this tritium on there. And what's interesting, most of these isotopes are radioactive, okay? And they give off small amounts of radioactive energy. Carbon-12 is not radioactive, but carbon-13 and carbon-14 are. That means they are going to decay and actually turn into different elements as neutrons are given off and converted into protons. And we'll talk a little bit more about carbon-14 and its importance and how we use carbon-14 and other radioactive elements in class. Well, that's it for today, guys, and I hope you enjoyed lecture number 3. Thank you.